Good morning, guys.
Good morning.
Looking forward to a relaxing and possibly productive weekend. Yeah. Can you hear me?
Yes.
Thank you. Yeah, I just submitted a grant proposal, so it's been the last couple of weeks have been pretty hectic, but it's all done. All right, so what is it today? Friday, October 16th. We are talking about we are discussing chapter 7, which is carbohydrates. And we talked about monosaccharides, and we're going to talk a bit more about monosaccharides and specifically about their cyclic form. So I'm going to share my screen. All right. So one thing I want you to recall from organic chemistry, OChem 2, is this reaction, the reaction between aldehydes and alcohols. So here, remember that aldehydes and ketones, they're electrophiles, and alcohols are nucleophiles. So the alcohols can attack the carbonyl of aldehyde or a carbonyl of a ketone, right? So if they attack the carbonyl of the aldehyde, we form a structure known as a hemiacetal. Hemiacetal, where the carbon that originally had the double bonded oxygen on it now has a free OH and has a carbon oxygen bond with the alkyl group coming from the alcohol. That's why it's called hemiacetal. Now, but the reaction can proceed further. And so the second molecule of alcohol comes in and replaces the OH with the alcohol group. And so you form a structure known as acetal and molecule of water, H2O. So remember, so you can go from aldehyde to hemiacetal to acetal. The same works with ketone. So here alcohol can attack the carbonyl to form hemiketal in this case, and ketal. Hemiketal and ketal. And again, it can go back and forth. That's important to keep in mind, right? The reaction is fully reversible. So we studied this as one of the main reactions in that ketones and aldehydes undergo. So for us, what's important, why are we talking about this in this chapter, is because these reactions form the basis for cyclization of sugars. And as we will find out, sugars exist in a cyclic form. And this chemistry explains that. Let me get actually a blue pen. So here's what's going to happen. So let's look at the structure of D-glucose. So we'll look at that last time. Remember the hydroxyl is on the right. So it's a D sugar. So you can bend this. Now remember, this is Fischer projection. And you can go from the Fischer projection into what's known as a Haworth or Haworth. I don't know how to pronounce it. Haworth form. So why do we need this Haworth form? You can see what's happening here is we want this alcohol to attack the carbonyl and to form hemiacetal. And so we need to bend this molecule in such a way that this oxygen is close to the carbonyl. And when this then attacks the carbonyl, you form a ring. You form a ring, and in this ring, the hydroxyl group right here, it can be up, right? Can be up, or it can be down. Or it can be down. And so the names of these new cyclic structures will be alpha D-glucopyranose and beta D-glucopyranose. So you already know D, right? You know D. You know gluco comes from glucose. You don't know the pyranose yet. We'll just find out in a second. What is new for you as well is this alpha and beta. So the rule that we follow, I think it's on the next one, next slide. So this carbon here, carbon that was the carbonyl, is known as anomeric carbon. Anomeric. Carbon. And these two structures, alpha and beta, they're, now, first of all, you may have noticed that they're epimers, right? So we talked about epimers last time. Remember that there are stereomers, which differ by the stereochemistry of one stereocenter. But these particular epimers are also anomers. Anomers. Because they differ in their stereochemistry at the anomeric carbon. This is anomeric carbon, and this is anomeric carbon. Okay. All right. So I think, okay, yeah, the next slide explains alpha and beta.
Dr. Corniaco?
Yeah.
I was wondering, so you said that the two were epimers and diastereomers, but I could be wrong, but I thought we said that epimers were enantiomers.
No. So epimers are diastereomers that differ by the stereochemistry of just one stereocenter.
Okay, thank you.
Enantiomers will be two compounds which differ by the stereochemistry of all stereocenters. So to go from one enantiomer to the other, you have to invert every single stereocenter.
Okay, that makes sense. Thank you so much.
Yeah, if you invert just one, it's epimer. If you invert more than one, but not all, those are just diastereomers. Yeah, a lot of different words, but keep practicing, guys. A lot of this stuff is in the sapling, right? And if you have questions, just throw them in the discussion forum. All right, so I think the hardest part here is actually, all right, so alpha and beta. Alpha and beta are not the hardest part. So which ionomer is alpha and beta? So the hydroxyl group, if it's on the opposite side of the CH2OH, then the configuration is alpha. If they're on the same side of the CH2OH, so the opposite trans, same cis, then it's beta. So let's go back to this. So you can see here, OH and CH2OH. Okay, that's the, remember, that's the carbon we're looking for. That's the carbon 6. And you can see they're on the opposite side, right? So CH2OH is up and the OH is down. So they're on the opposite sides, and that's why it's alpha. Now this CH2OH and OH are both up, the cis, right? cis. And then the configuration is beta. So alpha and beta anomers. And but one thing to keep in mind is that this structure is not frozen. We talked about the fact that this is going to be an acetal, that the acetals, their formation and decomposition is reversible, right? So for example, if you form beta D-glucopyranose, it can go back. It can go back to the open chain form, and then recyclize in such a way that your OH will be down. So in other words, there's a constant equilibrium between OH up and down. And so the two anomers are interconvertible unless you freeze them somehow. And we will find out how to do that in a moment. So as far as the hardest part in this whole thing, and I threw some Saplan problems for you to practice. The hardest part is to go from the Fisher projection to Haworth form. So in other words, can you convert this Fisher projection into this semi-cyclic form? I think this comes down to your skill as far as drawing the Fisher projections, right? So remember, so this is carbon 1. So you'll be standing. So this is you right here. And you'll be looking at this carbon from this direction. Right? And for you, it's almost like you're going to be lying down along this backbone and bend yourself, right? And so this is going to be your head here, and your feet are going to be down there somewhere. And your stomach, your belly button here, your shoulders are here somewhere, right? And so what you're going to see, so you go with your eyes, you're going to look at this, you're going to see that carbon of the carbonyl. Then you look at carbon 2, and what do you see? You see the OH to the right and H to the left, right? And that's what we have here. OH to the right, H to the left. Then we go to the next carbon. Now the switch, OH to the left, H to the right. That's carbon 3. Carbon 4, OH to the right, H to the left. And the hardest of all is to figure out the C5 stereochemistry here, right? So why do I draw the CH2OH up? Why not down? So I think the problem here comes from the fact is that in my chain, in my Haworth form, carbon 6 should be here, right? Carbon 6 should be here, but I switched OH and carbon 6. So it's not really clear now where carbon 6 is. Is it up or is it down? And so what you can do is, let's say we want to go from the Haworth form to Fisher form. And what I will do is I will redraw this cyclic form, Haworth form, CH2OH. That's my carbonyl. My OH hasn't changed, still down. Carbon 2, H is up. Carbon 3, OH is up. H is down. Right, carbon 4, OH is down. H is up. And now the challenge is, so if I turn CH2OH this way, what happens to this H? Where is that going to go? Is it going to be up or down on carbon 6? Sorry, carbon 5.
Up.
So I have two positions. I have this position and this position. So you said something?
I said up.
Up, that's correct. So CH2OH going clockwise, and then H will go up clockwise as well, right? And OH will also go clockwise, but it's going to go down, like so. And then if I continue looking if I'm going to continue converting this into the Fisher projection, again, OH right, OH left, OH right, and OH right again. So my two OHs are both on the same side, right? So the OH on carbon 5 is to the right. That's carbon 5.
So do we always do it that way for carbon 5?
Yeah, so that's going from the cyclic form to the open form. But obviously to do it from the, to go from the open form to the cyclic form, you will do the opposite, right? You will put the OH down and CH2OH up. And remember how you can manipulate the Fisher forms. Basically, you will need to exchange positions of all three of them. So rotate, right? So this is something for you. If you do not remember the Fisher forms, please OChem 2. No, OChem 1, I'm sorry. OChem 1. Review Fisher projections.
Would there ever be an instance where the OH was up on the 5th?
Yes, there will be an instance. And now tell me if that's going to be a D or L sugar.
Okay. Oh, okay. Yep. Now I see it.
Right.
Mhm.
So this is very common for D sugars, but if your CH2OH is on the bottom, right, then the OH will end up on top. So in that case, it will be an L sugar. We'll look at some structures of L sugars as well. Remember, for D sugars, in Fisher projection in a D sugar, your OH has to be on the right. In the cyclic form in a D sugar, the CH2OH has to be on top. So that's the best way to tell apart D sugars and L sugars. In the cyclic form, just look for CH2OH, 6 carbon. If it's on top, that's a D sugar. Bottom, L sugar. But it will come up again later in today's lecture. All right, any questions? There's a lot of stuff here. But you can see that if you pay attention, if you go over this a couple of times, or maybe you don't have to go over a couple of times, maybe you already got it. So it's pretty logical, right? And explains all these nuances of sugars pretty well. Nothing left unexplained. All right. So you know anomeric carbon, you know alpha and beta. And so the pyranose, and there will be also furanose. And that actually comes from the fact that there's a heterocycle. Remember, heterocycle is a ring where not all atoms are carbons. And so they have a heteroatom. So here, in this case, it's an oxygen atom here. So this ring is known as pyran, and this ring is known as a furan. And so it's a 6-member trin with the oxygen, pyran, a 5-member trin with the oxygen, furan. So the sugars which are based on a 6-membered rings with oxygen are pyranoses, and sugars which are based on 5-membered rings with oxygen are furanoses. So we'll look at that in a moment, and to jump in a bit ahead, fructose is a furanose. And it's right there actually. All right, so let's go over the structures again. So this is the ring form of glucose, right? So what do we have here? First, we know it's glucose. And one way to to memorize the structure of glucose, maybe you have to do it a couple of times, and then it will stick. Remember the anomeric position? This can be up or down. And it doesn't change the fact that it's a glucose, right? So both, so this will be alpha, and this will be beta. And why is it alpha? It's because OH and CH2OH, opposite, trans. That's why it's alpha, right? And it doesn't change the fact that both of these are glucose. So this is on this side, and this is on the same side. This is cis, and it's also gluco. Only in this case, it's beta, alpha and beta. Now both of these, both of these forms of glucose are D, obviously, because CH2OH is on top, and pyranose is because it's a six-membered ring coming from pyran. Now, this is fructofuranose, so the other component of table sugar of sucrose. So what we're looking for, fructose is actually a ketose. And so the anomeric carbon is this one. And how do we know it's an anomeric carbon? Well, it's a carbon that has 2 bonds towards oxygens. So it's a hemiketal, right? This is hemiacetal, right? And this is hemiketal. Hemiketal, anomeric carbon, hemiketal. And so position 2, 3, 4, 5. Now again, it's a D, right? Because CH2OH is on top. And this is alpha form because the OH at the anomeric carbon is down compared with the CH2OH, which is up. So alpha D fructofuranose, and it's furanose because of the furan. And so for glucopyranose, so the easiest way to to memorize the structure. So as I mentioned to you, alpha and beta can change. You just have to look on if it's up or down. But then look, carbon 2 OH down, carbon 3 OH up, carbon 4 OH down, carbon 5 CH2OH up. Right. So for glucose, it's very easy to memorize because they're all the substituents alternate their orientation. Okay. All right. And you can see this is beta because this and this are cis. And this is alpha. This and this are trans. All right, so remember in these pyranose forms, the sugars are chairs, right? They adopt the chair conformation. And remember the difference. Now, so there are 2 possible chair conformations. Which one do you like better? The one on the left or the one on the right? Which one do you think has lower energy?
The one on the left.
And why?
Because the bigger groups are equatorial.
That's right. All these substituents, OHs, right, they're equatorial. Probably that's why glucose is the most relevant monosaccharide, is because it can adopt a chair conformation in which all substituents will be equatorial. And these ones are axial. And in the axial form, remember there is a bad interaction. Do you guys remember why axial form is bad?
Sterics.
Sterics, and there's a specific type of interaction. So there's this one. It's known as a 1,3 diaxial interaction. All right. All right, so these are examples before we move on to disaccharides. Let's go over some important monosaccharides. So these are derivatives, right? So we talked about epimers, we talked about anomers, and so on and so forth. But let's talk about a little bit about derivatives in which not all substituents are oxygens. So, so these are going to be from the glucose family, right? Just from the glucose family. See, there's a whole bunch of them. All are important. So this is glucose. Remember, it's beta because OH is up. It's D because CH2OH is on top. And so this is beta D glucose 6-phosphate. So very important derivative. Basically, it's the first intermediate in glycolysis, right? So there is a glucose 6 kinase, the enzyme which is which phosphorylates glucose and traps it in a cell, right? So remember, glucose can go in and out of the cell, right? If it's in the bloodstream, it can go in a cell, can come out. But if it's committed to glycolysis, committed to production of energy, then it undergoes phosphorylation. So the question for you, so why does phosphorylation trap glucose in a cell? Why can't it come out anymore? Look at the charges. The charges is the key.
It makes it a negative.
So it's charged negative, and so what does that do?
It can't cross back through the membrane.
Yeah, it cannot cross the cell membrane. Remember, cell membranes are highly hydrophobic, lipophilic, right? And so they do not allow the passage of charged molecules. And so glucose 6-phosphate gets stuck in a cell and will undergo glycolysis. All right, so glucosamine. So that's a compound in which the OH is converted to NH2. And there's also N-acetyl glucosamine, where basically this NH is acetylated. So you have an amide. So it's an amide. Right, so glucosamine is an amine, and this is an amide. And so by themselves, so they are not as important, but they are derivatives of more important molecules. I mean, they're starting materials. So for example, muramic acid. And muramic acid is the compound in which the R group here is lactate. So it's a derivative, it's extension of a lactic acid. So it will be muramic acid. And if you acetylate it, it's N-acetylmuramic acid, and abbreviated as NAM. And if you remember, we talked about NAM and NAG. Anybody remembers NAM and NAG?
Lysozyme breaks it down.
Lysozyme, yep. So that forms the bacterial cell wall, right? Bacterial cell wall. So it's an important constituent of bacterial cell wall. So that's also a glucose derivative. Now, there's a bunch of, so there are actually two ways to oxidize glucose. There is, you can oxidize position 6, in which case it will be glucuronate, or glucuronate. And you can also oxidize position 1, in which case it will be gluconate. Now, this can undergo an ester formation, so this will be an ester. And remember, if you have a cyclic ester, cyclic esters are known as lactones. Lactones. And so, for example, this one is a D-glucono delta lactone. And guys, why is it delta? Anybody knows? What does delta mean? So there are different ways to form lactones, right? For example, you can form a lactone with that OH. You can form a lactone with that OH, right? But if you label carbons, alpha, beta, gamma, delta, then it's a delta OH, delta hydroxyl, which will form the ester bond with the carbonyl. So it's a D-glucono delta lactone. All right, then galactosamine, right? So remember, galactose is the C4 epimer. So that's the difference here and here. C4 epimer. So they differ by the stereochemistry in carbon 4. So it will be galactosamine. So for mannose-amine, all the OHs are in place. It's just that the amino group is on top. So beta D mannose-amine, right? So it's derived from mannose. So instead of the OH here, we have NH2 derived from mannose. Okay, here are some examples of L sugars. These are actually a little funny because they don't really have OH on carbon 6. So this one is a beta L fucose. And also why it's, so basically it's L because the CH3, which is carbon 6, right, is on the bottom. And also note that normally when we look at glucose derivatives, for example, we say that this is beta glucose because OH is on top, right? But it's not so much that OH is on top, it's because OH and CH2OH are cis. And here is where this rule becomes important. You can see in L-fucose, this OH derivative is also beta, even though the OH is down. You see, this OH is up and is beta. This is OH is down and is beta. But it's beta because the OH and the CH3 group are on the same side. So cis. And here we have a rhamnose. It's also L rhamnose. You see carbon 6. CH3 is down. But now it's alpha. And it's alpha because CH3 and OH are trans. right? So just by looking at the OH to see if it's up or down at the anomeric position, you cannot tell if it's beta or alpha, even though it's highly attractive way to to name these compounds, because you would think, you know, it's easy, right? But not necessarily. You have to look at carbon 6, right? And it's only beta. The up one is only beta if the carbon 6 is up. If the carbon 6 is down, it could be beta or alpha, depending where the OH is. All right. And finally, there is N-acetylneuramic acid, also known as sialic acid. We're going to spend some time talking about that. Very important carbohydrate on the surface of cells. On the surface of cells. And it's highly overexpressed, for example, by tumor cells, cancer cells. And there is actually a lot of therapies right now being developed, which target specifically cancer cells because they have antibodies which bind to sialic acid. They have antibodies that carry drugs. So basically what you have is, so let's say this is your cancer cell, hopefully not yours, just a cancer cell. Let's say this is cancer cell. Cancer cell, so here is sialic acid. Right, sialic acid. And remember, antibody, well, the antibody will bind to sialic acid. And the antibody will bring a drug with itself. There will be cancer drug. Antibody. All right, and so this kind of therapy is known as ADC, and actually the number of such therapies already on the market. ADC stands for antibody drug conjugates. So very exciting area of research right now. A lot of money in this area. These therapies are quite effective. The only problem is they're highly expensive. Highly expensive because every time you have to attach a drug to an antibody, that's a very expensive process, right? So, all right, any questions about these? Okay, let's move on. Now, yeah, and so couple of important concepts. One of them is what's known as reducing sugars. Reducing sugars. So if you have a hemiacetal, so hemiacetal basically can easily open up to give you the aldehyde. And so we refer to this kind of hemiacetal as the molecule that has a free anomeric carbon. In other words, it's not a full acetal, just a hemiacetal. And so these hemiacetals can be oxidized by copper, known as a Felling's test. And Tollens test is a little more common. Yeah, I don't know so much about Phelan test, maybe historically more important. But Tollens test is very important because basically you take a salt of silver salt, you mix it with the sugar, which is reducing sugar, has a free anomeric carbon, and then you have a silver precipitate and you have a nice shiny, like a mirror on the bottom of the flask, right? So basically silver, metallic silver precipitates from the solution.
Dr.
And that's
Green,
because the sugars, such as reducing sugars, will reduce silver from +1 to 0. Sorry, you had a question?
would this also work on ketones if they go through tautomerization or no?
So ketones. So if you have ketals, yes. But it has to be hemiketal.
Right, if they tautomerize, right?
To tautomerize. Are you talking about this kind of tautomerization? So this is tautomerization.
Right.
So what's
So
the question?
Would that test work on that?
No, the ketones are not reducing agents. Basically, you need a reducing agent.
Okay.
You need a reducing agent. Ketones are not. You can't really oxidize ketone.
Okay.
Remember, ketones are quite stable towards oxidation. Aldehydes are not. And the reason for that is because aldehydes have this hydrogen. And aldehydes can very easily undergo oxidation to carboxylic acids. Right, so acetaldehyde will undergo oxidation very easily to acetic acid, but ketones will not.
Okay.
Okay. All right, and so there is a glucose sensor, biosensor, which is used by diabetics, which is based on this chemistry. So there is an enzyme known as glucose oxidase. So it utilizes, basically it grabs a molecule of glucose, right? Now it's important to have this free anomeric position. So remember, free is because here we have a hydrogen, not R, right? So it has to be hemiketal, not a ketal. Sorry, hemiacetal, not an acetal. If it's hemiacetal, then glucose oxidase can oxidize it to the lactone, so gluconolactone. And it utilizes oxygen. It will, the oxidation of glucose will result in the production of hydrogen peroxide. And then it utilizes a dye, which is in this form is just a faint orange, basically almost colorless. But hydrogen peroxide will oxidize this dye into this extended form, which is dianicidine, which is bright orange. And so by the brightness of this orange, you can actually quantitate how much glucose is present in the sample, right? So technology is utilizing portable glucose sensors. So it's a biocatalytic oxidation, right? So you have it's an enzymatic reaction. All right, so yeah, there's we still have some time. All right, so the two molecules obviously can be joined by the glycosidic bond. So when we talked about the anomeric carbon, we can talk about hemiacetal, and we talked about full acetal. So the full acetal is when you have the second molecule of alcohol coming in and forming what's known as a glycosidic bond. So do I have that? It's right here. Before we read the rest, let me just show you the figure. So let's say this is alpha D glucose, right? It's hemiacetal, and the alcohol now will be the part of another molecule of glucose. Another molecule of glucose, it'll come in, And remember, again, this can open up, or this hemiacetal can undergo the second reaction with another molecule of alcohol and form full acetal, right? So carbon 1 now is a carbon at which we have the acetal functionality. And so now we have two sugars joined together. So this particular sugar is known as maltose. So maltose is the sugar in which two glucose molecules are joined together. Now this is disaccharide now, yes, disaccharide. And this is how we're gonna refer to this. So first of all, let's name the component on the left. So it's alpha. It's alpha because of the, now this bond is kind of looking funny, but it's just a way for us to show that these two are linked, right? But obviously this bond will be straight down. So with sugars, you kind of have to get used to these kind of funny bonds. So sugar chemists don't notice that anymore. But when you see it for the first time, you start wondering, what is that? So it's just a way for us to show that these two monosaccharides are linked through the acetal bond formation using this oxygen atom. All right, so it's alpha, it's down, compared with CH2OH. It's D, then it's glucopyranosyl, right? And then we have this important pointer which tells us which positions are linked. So carbon 1 on glucopyranosyl is linked with carbon 4 of another D-glucopyranose, right? So it's 1 through 4. So you start with an anomeric position and you end with the position where the alcohol is coming from, that's carbon 4, and you end with the structure of the type of sugar that it is. And notice, as tell me, now we form the disaccharide. Is this a reducing sugar?
Yes,
And what tells you that?
because there's a free anomeric carbon on the right.
Yes, there is still free anomeric carbon. Now, it's no longer this one, even though glucose is a reducing sugar, right? It's hemiacetal, but we blocked this. We went from hemiacetal to full acetal. So we went from from reducing position to non-reducing position. But we added another molecule of glucose, and it still has a reducing position on the right. So let me see what we say here. So glycosidic bond. What is glycosidic bond? This is the glycosidic bond. Glycosidic bond. So remember that word. It's not glucosidic bond. There's no such thing. It is glycosidic bond, which will be similar for all kinds of trisaccharides, oligosaccharides, and polysaccharides. All right, so glycosidic bond between monomers. So it's more stable, less reactive than hemiacetal. Okay. Second monomer with hemiacetal is still reducing. We just decided that. And then anomeric carbon involved in glycosidic linkage is non-reducing now. Now, disaccharides can be named by the linkage 1 to 4 glucopyranose. So the common name for this disaccharide is maltose. Okay, let's look at a couple more of these. So now these are non-reducing disaccharides. Why they're non-reducing is because if you link them through anomeric positions of both monosaccharides, basically you eliminate both reducing positions. There are no longer, so not here. If you eliminate both reducing positions, then there's no longer reducing position left. So sucrose, for example, is a non-reducing sugar. Now lactose is still a reducing sugar. Why? Because of this free anomeric position. So lactose, let's see how we read lactose. So it's again, it's beta, because the oxygen of the anomeric carbon is up on the same side as CH2OH. So beta D galactopyranosyl 1 through 4, carbon 1 to carbon 4, beta D glucopyranose, right? So it's again, it's a beta OH is on top, it's D CH2OH on top, glucopyranose. Now there is a shorter, now you don't have to write this out, right? There is a, just like with the amino acids, there is abbreviated form that you can use, and it's this. Basically galactose, it's a beta glycosidic linkage 1 through 4 to glucose. And usually for the glucose, you don't really say it's beta glucose because this can undergo interconversion with alpha. So it's not frozen. Now, this sucrose is a non-reducing sugar. You form non-reducing sugar basically when you join the two anomeric carbons. So in sucrose, table sugar, right? So we still have beta D. Okay, we'll start with the, it doesn't matter which side you start. How does it? No, it doesn't. You can see here, you can write it like this, or you can write it like that. Because they're both anomeric, right? So we start with anomeric, but they're both anomeric. So it doesn't matter which side you start from. So let's start with the fructose first. So it's a beta, because CH2OH and this anomeric glycosidic oxygen on the same side. It's D. It's D. Because if it's, I guess it's upside down. If you turn it the right way. No, wait. Hold on a second. Yeah, this is an anomeric position. This is carbon 6. Carbon 6, if you turn this upside down, it will be on top. So beta D fructofuranosyl, so furanose, and then alpha D glucopyranoside. And you can write this as a fructose, position 2 beta, which is linked to another anomeric carbon. That's why it's this kind of arrow, right? It's not that kind of arrow. This kind of arrow takes you from the anomeric carbon to non-anomeric carbon. But since both carbons are anomeric, so it's going to be this kind of arrow. Yeah. And 1 alpha, 2 beta on this side, 1 alpha, glucose. Now trehalose is a disaccharide of the 2 glucose molecules, also linked through their anomeric carbons. It's also non-reducing. So this one is reducing, non-reducing, non-reducing. Any questions from today? No? So there is one more lecture on Monday for this material. And we're going to talk mostly about we'll talk more about disaccharides, polysaccharides, and various glycosylated molecules in biological systems. We should have enough time. All right. Have a good weekend, guys.
You too.
Thank you.
Yeah, bye.